Hey everyone, welcome to ILTA Physics Problem Solving. Physics can feel a bit overwhelming at first, but if we break it down step by step, it's actually pretty straightforward. Today we're going to be talking about angular kinematics and rotational motion. To describe rotational motion effectively and efficiently, we've defined a new set of kinematic variables. Specifically, when it comes to the angle an object has rotated, we don't use the degrees we use in everyday life. Instead, we use a unit called the radian, which is based on the geometric properties of a circle. We're going to solve some classic angular kinematics problems using these concepts. If there's anything in the text you don't quite understand, I highly recommend going back to the related lecture video to get a solid grasp of the concepts before trying the problems again. Alright, let's quickly summarize the core concepts that serve as the foundation for solving angular kinematics problems. The problems we're tackling today involve rotational motion where the velocity is constant, meaning there's no change in speed. We call this uniform rotational motion. There is really just one fundamental formula used to describe this. The rotational velocity of an object, or its angular velocity, is the change in angular position divided by the time interval. The unit for this is radians per second. Here, the change in angular position, or angular displacement, is the final angular position minus the initial angular position. By rearranging the definition of angular velocity, we can also express this as the product of angular velocity and time. In this context, theta represents the angular position of the rotating object. So far, we've covered the physical definitions and formulas for rotational motion. However, in actual problems, the rotational speed of an object is often given in units other than radians per second. The first one is RPM, which stands for rotations per minute. It tells you how many full circles the object makes in 1 minute. To convert this to radians per second, you take the RPM value and multiply it by 2 pi divided by 60 seconds. The 2 pi in the numerator represents the angle of one full rotation, and the 60 seconds in the denominator converts 1 minute into seconds. For example, if you have 78 RPM, you would calculate 78 times 2 pi divided by 60 seconds. Depending on what the question asks for, you can either leave the answer in terms of pi or multiply it out using 3.14. Another unit often used for rotational speed is revolutions per second. Just like the name suggests, it tells you how many laps the object completes in 1 second. For instance, to convert 5 revolutions per second into radians per second, you simply multiply 5 by 2 pi. In other types of problems, you'll be given various conditions describing the rotational motion and then asked how many total rotations the object made or what its final angular position is. You can find the number of rotations and the final angular position by taking the total amount of angle of rotation and dividing it by 2 pi. When you calculate the total rotation in radians and divide it by 2 pi, you'll usually get a number with a whole part and a decimal part. The whole number tells you the total number of full laps the object completed since one full revolution is equal to 2 pi. The decimal part is a little bit tricky. The decimal part, when multiplied by 2 pi, gives you the object's final angular position, which will be a value between 0 and 2 pi radians. Also, in uniform circular motion, you're often asked for the object's velocity in the tangential direction, its tangential velocity. The tangential velocity of a rotating object is calculated using the formula angular velocity times the radius. As you can see in the diagram, angular velocity is the speed of rotation along the circular path, while tangential velocity is the speed of the object moving in a straight line at that specific moment. Make sure you fully understand this through the related online lectures. Finally, there are problems that ask for the total distance traveled by a rotating object, like a wheel. I'm sure you all know the physical difference between distance and displacement, right? If you're confused about this, please watch the online lecture for the previous unit before trying these problems. In rotational or circular motion, the total distance traveled is calculated by multiplying the circumference by the number of rotations. Now let's jump in and solve some representative problems together. Problem number 7 says a small piece of dust has fallen onto a turntable spinning counterclockwise at 78 RPM. The initial position of the dust, meaning its position at t=0, is 0.45 radians. The question is, where is the dust located after 8 seconds? The problem asks for the final position to be given as an angle between 0 and 2 pi. In the problem description, the parts highlighted in red are the given conditions. First, the rotation speed of the turntable is given in RPM. So we need to convert that into radians per second. As I explained earlier, we multiply the RPM value by 2 pi radians divided by 60 seconds to get the angular velocity in radians per second. Since we find the final position of a rotating object by dividing the total rotation angle by 2 pi, let's find the total rotation angle first. The angular displacement over 8 seconds is the angular velocity multiplied by 8 seconds, which comes out to 65.344 radians. One thing to be careful about here: since an initial position at t=0 was given, the total angular position including that starting point is 65.794 radians. Now if we divide that total amount of rotation angle over 8 seconds by 2 pi, we get 10.471. The whole number 10 represents the total number of full rotations. Since the question is asking for the final angular position, we take the decimal part, 0.471, and multiply it by 2 pi. That gives us the final angular position of the dust in radians. Among problems involving angular motion of an object, a very common type asks you to represent the motion on a graph. These test whether you can interpret the object's rotation by looking at the visual data. Problem number 9 is a great example of this. The graph on the right describes the rotational motion of an object. When you see a graph, the very first thing you should do is identify exactly what physical quantities the x-axis and y-axis represent. This specific graph shows the change in angular position over time. If we look at the overall motion, it starts at an initial angular position of 25 radians. For the first 10 seconds, it rotates counterclockwise at a constant speed. And for the following 10 seconds, it rotates clockwise at a constant speed. What we can tell from the graph is that the rotational velocity is constant in each interval because the slope of the line is constant in each interval. Also, we can tell the direction of rotation by whether the slope is positive or negative. If this isn't clear to you, please review the lecture material before moving on with the problem solving. The first part of the question asks for the change in angular position, the displacement, between 5 seconds and 15 seconds. Angular displacement is calculated by subtracting the initial position from the final position. Looking at the graph, the position at 15 seconds is 62.5, and the position at 5 seconds is 50. So, 62.550 equals 12.5 radians. Please make sure you understand that angular displacement is different from the actual distance traveled. The second question asks for the angular velocity at the 15-second mark. As we saw in our main formula, angular velocity is angular displacement divided by the time interval. In this problem, the rotational velocity is constant between 10 and 20 seconds, so we'll use the values from that interval to find the velocity. The change in angular position is the position at 20 seconds, 50, minus the position at 10 seconds, 75. The time interval is 20 minus 10 seconds. So the rotational velocity in this section is minus 2.5 radians per second. It's important to understand the meaning of the sign here. Angular velocity is a vector quantity, meaning it has both magnitude and direction. A negative value means the object is rotating in a clockwise direction. The last question asks for the maximum speed at a point 15 centimeters away from the axis of rotation. The problem doesn't explicitly state whether it wants angular speed or tangential speed, but we can infer its tangential speed because it provides a specific distance of 15 centimeters. Angular speed is the same for every part of a rotating object, regardless of the distance from the center. Since tangential velocity is calculated as angular velocity times the distance from the axis, we need to find the angular velocity first. As we observed earlier, there are two different rotational speeds in this motion. If we calculate the angular velocity for each section, we get two different values. Regardless of the direction, the maximum angular velocity is 5 radians per second. Multiplying this by the distance of 15 centimeters gives us a tangential speed of 0.75 meters per second. Even though the formulas we use are very simple, it's absolutely necessary to practice understanding the given conditions and applying them correctly. That's it for today's problem-solving session. Great job, everyone.